Hello students, in this video I'd like to cover the topic of paramagnetism and diamagnetism. And before we get into the details of this, I just want to state right here at the beginning that we are not talking about ferromagnetism. Ferro, meaning iron, is a different type of magnetism from this. So that we're not talking about, this is not ferromagnetism. Ferromagnetism is the kind of magnetism that you experience when you have an actual magnet and you can attract iron and steel with it. That's ferromagnetism. We are talking instead about paramagnetism and diamagnetism. Now, all elements exhibit some magnetic properties due to the presence of their orbiting electrons. Anytime you have an electric field, and with electrons you have an electromagnetic field, you will have some degree of magnetism. Any elements with no unpaired electrons, that means that all the electrons are paired up in their ground state. So when you write their electron configurations, every electron is paired up. They are called diamagnetic. So diamagnetic, all electrons are paired up. Another way to remember this is that di means two, so all electrons are in dyads or are in pairs. When you have an element that has no unpaired electrons, they're diamagnetic, and that element, those atoms, will be very weakly, and I mean very, very weakly, repelled. Repelled by an externally applied magnetic field. So if you intentionally induced a magnetic field and you placed this element into it, the atoms would be very weakly repelled by that field. And this is a very, very weak repulsion. It is so weak that generally you cannot feel it, and instead we need instrumentation to be able to detect it. So in contrast to diamagnetic, paired, every electron being paired up, elements that have at least one unpaired electron are called paramagnetic. P-A-R-A, magnetic, paramagnetic. And paramagnetic atoms will align with an external magnetic field. They will line up so that if the magnetic field were in this direction, then the atom would align with that field. And that occurs with paramagnetic atoms, where in their electron configuration, they have at least one electron that is not in a pair. So with that in mind, we have two new terms, diamagnetic and paramagnetic, and a practice problem. So in this practice problem, it says, based on their electron configurations, circle all of the following elements that are expected to be diamagnetic. Diamagnetic means what? All electrons are paired. There's no unpaired electrons. Diamagnetic in their ground state. In their ground state, that phrase just means before electrons are promoted to some excited state. So the ground state is the electron configuration that we normally write. So we're looking for diamagnetic elements. We're looking for elements where the electrons are all paired up. I'm going to do a couple of these, and then I'll let you do the rest. So let's deal with hydrogen first. And I want to remind you that we have already done the electron configurations for all of these elements. So if we go back a couple of pages, here's the electron configurations for hydrogen and helium. And then we have lithium, oxygen, bromine, tantalum, silicon, barium, and then we had chromium, silver, and gold at the top of this page. Okay? So we have already done the electron configurations for all of these atoms. And if you had not already done that, then in order to answer this question, you would have to do those. So let's start with hydrogen here. Is hydrogen diamagnetic? Well, what is diamagnetic? It means that all of its electrons occur in pairs. Well, we know hydrogen cannot possibly be diamagnetic because it only has one electron. So if we go back and look at hydrogen's electron configuration, hydrogen only has one electron right there, And so it is definitely not paired up with another electron because there's only one electron there. So hydrogen is definitely not diamagnetic because it does not have its electrons all in pairs. So we would not circle hydrogen. Moving on, helium. Is helium diamagnetic? Does helium have all of its electrons in pairs? And we can see that there are 2 electrons in helium, and they are both in the 1s subshell. And if you recall, they are indeed paired up. So helium is indeed diamagnetic. All of its electrons occur in pairs. So we would circle helium. Okay, so I'm going to let you do the others, but before you do that, I want to give you a little warning. And the warning is, if you just look at these numbers of electrons and you see even numbers, that may or may not tell you whether they are paired. You can have even numbers of electrons, but they may not be paired up. And I'll give you an example. Here's oxygen, and notice that we have all even numbers, but that does not mean that these electrons are all paired up. So keep that in mind as you look at the rest of these elements to determine if they're paramagnetic or diamagnetic. And for this question, you're just going to be circling them if they are diamagnetic. Okay, so now go ahead and do the rest of this problem for the rest of these elements. Pause the video, complete this work, and when you're done, resume the video, and I will continue on and give the answers for this. All right, coming back from pausing the video, we're going to look at lithium. And right away from lithium, we can tell that there are odd numbers of electrons in these subshells. If you have an odd number here, that is an absolute dead giveaway that you have electrons that are not paired. So any electron configuration that gives you odd numbers of electrons, we know those are going to be paramagnetic, where you have unpaired electrons. So lithium is paramagnetic. It is not diamagnetic, so we would not circle lithium. Let's get down to oxygen. And here's that pitfall I warned you about. We have all even electron numbers, 2, 2, and 4, but we're not going to let that mislead us into thinking that that means that they are necessarily all paired up. In fact, oxygen, you may recall, looks like this. We have 8 electrons overall. 1, 2, 3, 4, 5, 6, 7, 8. And because of Hund's rule requiring us to spread the electrons out before we paired them, oxygen does have an even number of electrons in each subshell, but in the 2p subshell, it has unpaired electrons. So oxygen is paramagnetic because it has unpaired electrons. So we would not circle oxygen. On to bromine. Bromine has an odd number of electrons in its 4p subshell, which means it is impossible for them all to be paired up, and so bromine is paramagnetic. The same thing is happening with tantalum, where we have an odd number of electrons in a subshell, and so we know that tantalum must be paramagnetic. Silicon. We have an even number here, but notice that there are 2 electrons in the p subshell, and we know that those 2 electrons would have been spread out before they would have been paired. So in the 3p subshell, 1, 2, we would have 2 electrons in the 3p subshell. So here again, you can see that though there are even numbers of electrons in each subshell, that doesn't necessarily mean that they're all paired up. In the case of silicon, they are not paired up. In the 3p subshell, we have electrons that are unpaired, and therefore silicon is paramagnetic. So we're not going to circle silicon. For barium, now we see that we have 2 electrons in the 6s subshell, and we know that any s subshell only has 1 orbital, so if you have 2 electrons, they must be paired up. The rest of barium's electrons are in the xenon core, and we know all of those electrons would be paired up because it is a noble gas with all subshells filled, and therefore all orbitals filled with the pairs of electrons. So barium has no unpaired electrons. All electrons are paired, and therefore barium is diamagnetic. So here we go. Barium would be circled. All right, that leads us to the last three, chromium, silver, and gold. And these three are examples of s promotion. And so we know right away, because these are s promoting elements, they're all going to have a single unpaired s electron in their valence outermost highest energy s subshell. So all three of these have unpaired electrons. All three of these are paramagnetic, and therefore none of them would be circled down here, because we're only circling the diamagnetic atoms. So here we go. We've only circled two of these for being diamagnetic. And now that we've done this, let's take a look and see if we can spot a trend or a pattern. On the periodic table, every time that you fill a subshell, you're going to have paired electrons. So once you get to helium, you're going to have a filled 1s subshell. When you get to beryllium, it will be a filled 2s subshell. When you get to neon, you will have a filled 2p subshell. So the general guideline here is that column 2, group 2, those elements are diamagnetic because they have all of their electrons paired up. The same is true for group 12. Once we get to these elements, we have paired up all electrons because we have a filled d subshells as well as the filled s subshells. And finally, when we get to noble gases, we have filled p subshells, and so those elements are also diamagnetic. Now I'm not going to talk about the F block down here because it's a little bit anomalous. These two, lutetium and lawrencium, these are not diamagnetic. And part of that is because of the way that we start the numbering here with cerium and thorium. But I should say that there has been recent research that may change the way that we write these F block elements. And they may eventually bring lanthanum down here and put it right here, and actinium down here and put it right here. And then lutetium and lawrencium would end up going up here. So for now, we're not going to include the F block in this trend. But what this means is elements in group 2, 12, and 18 are diamagnetic. Okay, so we can notice that as a trend or pattern.